So thank you for the presentation, and thank you everybody for joining today. As you can see, I have a cold, so my voice is not the best. I hope it will go through all the presentation and the questions, so yeah, let's keep going. So today I'm going to talk about some mathematical programming models and algorithms applied to the wind park problem. So this thesis is a collaboration between DTU and Vattenfall. So first of all, a few words about Vattenfall. Vattenfall is a big energy company. It's covering different kinds of energies, as you can see here in these slides, and is operating in all North Europe, in many countries here. Actually, we will focus only on wind energy, and in particular on offshore wind energy. So, as I said in the title, we're going to use optimization for the wind park design problem. So what is the wind park design problem? So when Vattenfall wants to build a farm, what they do is that they enter a tender. So practically, the state decide that they want to have a wind park in a specific area, and then different companies can enter competition to decide who is going to build the site. So in particular, so they have a higher area. For example, this is a real site called Danish Kriegers Flak in Denmark. The red boundaries were given by the state, and they decide that they want to have 2 wind parks located inside these 2 boundaries. And the blue dots you see over there are an already existing park nearby. So there are actually, this is actually a very long process to decide how to define a new park. And there are actually a lot of optimization tasks involved. In particular, we focus in my thesis in 3 optimization tasks that are the wind farm layout optimization, the inter-array cable routing, and the jacket foundation. So the first one is once you have an area, you have to decide where to locate the turbines in order to maximize the production of the park. The second point is once you have located the turbines, you have to decide how to connect them through cables. So the energy of the turbines offshore needs to be collected in some collection points called substations that are, in this case, in the red squares. And of course, you have to do it in a smart way so that you can save money on the cable costs. Oops, sorry. And we also consider the jacket foundation design optimization. So in some specific, so of course you can optimize how the foundation of those turbines are made. And in particular, we focus on a specific type that is the jacket foundations type. That is a kind of foundation, one of the most complex one used when the water is quite depth. I don't have time to go into these in the presentation, but I will focus on the first 2 only. So my thesis consists in a number of papers. Here I put them all together. And of course, I will not have time to go in depth in all of them, or some of them neither to touch upon them. So what I will present you today is this paper over here. So the optimization of the wind farm layout, where to locate the turbines, and mainly this paper that is about the main paper about the cable routing. So motivation, so how this PhD, industrial PhD started. So this PhD, as I said, is a very close collaboration with the company, Vattenfall. And in Vattenfall, they had this problem that is actually not only in Vattenfall, but in most of the energy companies operating today. So when they had to go through this design of a wind park, and in particular of the 2 tasks that I talked to you about, they had a very long process involving a lot of people. So first of all, they were having only some basic commercial software to optimize the position of the turbines. And this commercial software were including only some of the constraints actually arising in the practical applications. So what they were doing was to create an initial layout focusing mainly on production using commercial software. Then they were in the post-process phase checking a lot of constraints and maybe manually change the layout. So where they were doing quite some loops in this area. And once they had defined a layout that, of course, was quite suboptimal due to these manual changes, this was passed to another team. This is the electrical team. It was up to the electrical team to decide how to connect these turbines through cables, and this task was done manually. So there was an electrical engineer with paper and pen deciding by hand how to connect the turbines with the substation. Of course, doing it by hand, you cannot check all the constraints involved in this problem. So what they were doing here again was having a lot of loops. So they were creating a first layout, then they were verifying the different constraints and updating manually the layout many times. So of course you can already imagine that this process is very time consuming, involves a lot of people, and the final solution was highly suboptimal. So what we have done in this thesis is focusing on these two different packages and using optimization techniques to improve these tasks. So in this presentation, I will present you exactly these two packages, the wind farm layout optimization and then the cable routing optimization. Okay, let's start with the wind farm layout. So now I'm going to go a little bit more in details on what the problem is and what techniques we use to solve it. So the problem is to find a feasible allocation of turbines in a given area with the objective of maximizing the power production, which is the main income for the company. So as I already mentioned before, we are given the area that normally is given from a tender phase. And for example, this is an example of a real case. You can see the green area is the area that could be used to locate turbines, and there may be also some obstacles in the area. For example, here there were some cables existing, so we can locate only in the green area. We're given by the engineers of the company what kind of turbines we want to build in the area, so in particular how big these turbines are and how much they could produce, and of course we are given the measurements of the wind in the site. When we have to locate the turbines, we have to take into account proximity constraints, so I cannot locate turbine too close one with the other one, and also a maximum number of turbines that often translate in a fixed number of turbines that the company wants to locate in the site. Another very important aspect when we optimize the position of the turbines is considering the wake effect. So the wake effect is the phenomenon you see in this picture. And this picture is actually from Vattenfall, from a site in Denmark owned by Vattenfall, and there is no Photoshop. This is actually how you could see it in some specific wind scenario. So here you can see that the wind is blowing in this direction. So the first line of turbine is heated by full wind, so they can produce the maximum that model of turbine could produce. But all the turbines behind are actually in the shadow of the first ones. So that means that these turbines cannot produce their maximum, and they also are subject to a high turbulence. So if in this layout we wouldn't have the turbine in the shadow of the first one, but in a position out of these cones, we would be able to produce way more. So it's really important when we optimize the position of the turbine to minimize this wake effect. Okay, so this problem can be modeled as a MIP model. So what we do is that we take all the available area and we discretize it in a number of possible positions. For each of these possible positions, we have a variable, xi, that is equal to 1 if a turbine is built in that position, or is equal to 0 otherwise. So the problem that I stated before can be in a very simple way written as I wrote here, down here. So what we are doing is trying to maximize the production considering the interference. So if PI is what is called in wind energy gross production, so the production without considering the interference, so if the turbine was alone, I want to maximize the production of all the turbines I'm constructing, taking into account the interference. So if I build both turbine I and turbine J, I have to consider the interference indicated as IIJ of the two. So first of all, we studied the literature about this problem. There were a lot of continuous models that nevertheless are highly non-convex, are very computationally challenging, and it's very difficult to take into account obstacles in the site, which instead is something that happens very often in reality. So we decided to go instead for discrete models, and I'm reporting here the model from the literature that is closer to what we were asked to do by the company. So this paper by Donovan, 2005, takes the function that I told you before, the immediate one, let's say, and rewrite it using a Zij, so a double index variable, which is good because it managed to have the problem written in a linear way, so this is a mixed integer linear programming, but you have a variable with double index. What we did instead was to use a different way of modeling this problem. So if we go back to our, let's say, naive way of writing, immediate way of writing, where we have the square in the objective function, xj multiplied by the xi, what we did instead was restating it using a single variable, wi, that represents the total interference caused by a turbine position in position I. So in our model, therefore, we have a single index variable that represents indeed the interference. So this is the model that we proposed, where, of course, we are maximizing the total power production considering the interference. We have a minimum maximum number of turbines to build. We have a minimum distance between turbines, so we have incompatible pairs if they were too close. And we have a big M constraints that define the WI model, so the WI variable. So comparing with the model from the literature, this model seems to perform better. The model from the literature was able to solve problem until 100 possible positions. With this one, we managed to solve until more or less 1,000 possible positions. So another advantage of these models is also that it's very easy to take different wind scenarios into account. So of course, when we build a park, we locate the turbines in a specific way, and that's it. So if the wind change, we cannot move the turbines around. So when we optimize their position, it's very important for us to consider all the possible wind scenarios in the site. And it can be seen that the model that I showed you before, the stochastic programming variant of the model that I showed you before, simplifying simply considering the weighted average of the power production over all the possible scenario and the weighted average of the interference over all the possible scenario. So this is very good because we can use the model exactly as I showed you in the previous slide, also in the stochastic programming variant. By simply using PI and IIJ as weighted averages, which is really important because in practical cases we are dealing with 100,000, even more possible scenarios for each side. Okay, so we were very happy about this model. We went to the company, we said, oh, we have something really cool, let's use it. And they give us a possible site with 10,000 or 20,000 possible positions. So we said, okay, no, maybe we're not ready for this. And we went back to our room and we started to study again what to do for these bigger cases. So the problem is that we want to solve in a feasible amount of time, so in a few hours, let's say, or a few minutes, some cases with a lot of possible position. So the solution we found for this problem was to use a math heuristic approach. So I don't have much time to go in the details of this methodology, but our idea is we developed some ad hoc heuristic, mainly based on one-opt and two-opt heuristic adapted for this case, so with the minimum maximum number of turbines and so on, and pay attention of trying to avoid local minimum, to generate a first feasible solution or first good solution. And then we use the MILP solver as a black box to try to search in the neighborhood of these solutions. So what we use is a technique called proximity search, which idea is exactly to change the model so that CPLEX, or the MILP solver you would choose, will look in the neighborhood of the solution. And we iterate this process every time we find a better solution. So this method that we propose seems to work very, very well. So in these graphs, you see two different instances. One has 5,000 possible positions, and the other one has 10,000 possible positions. We are comparing the approach I just told you, called proximity search in black, with three other alternatives. So the blue one is local search, so just using basic heuristics. The green one is using the initial model that I presented you with the CPLEX in this default setting, and the red one is using CPLEX with some more advanced settings for push-a-bit heuristics. So in this graph, you see time on the x-axis, versus profit on the y-axis. So the highest, the better. And you can see that our approach in black is able already to find a very good solution pretty fast. We are here about 300 seconds, and it's always outperforming all the competitors. So, as I said, this software has been used by the company. So I want you to show you a real case of application. And I'm showing you here a Borsele site where this software was validated. So this is a real site in the Netherlands. Was actually divided in 4 different areas, and we will focus only on area number 1. So this is the feasible area that we had. So we can locate turbines in all the green area. And we were asked by the company, in this case, to locate 50 Siemens turbines with a minimum distance of 5 rotor diameters. So this is the solution. The colors in the background represent the interference, and the dots represent the built turbines. So we compared our solution with the solution that Vattenfall would have found without our software. That is a solution obtained by the commercial software. So in blue, you can see the location of the turbines that Vattenfall found through this commercial software, and in red, the one that we propose. These 2 layouts have been evaluated by the third software that actually simulates the wake effect in order to understand their production. And we have seen that our layout is about 0.57% better in annual energy production. That it seems little, but with this amount of money is actually about 6 million euros, so it's a big impact from a company perspective. Another nice thing for the company of using our software instead of the commercial one is that we can consider, for example, cost of foundation in the optimization. So when we optimize the position of the turbine, depending on where we locate the turbine, we can have a different production, but we can have also different costs to actually build this turbine. So this is an example of cost map for this specific site. So you can see that there are some areas where it's more expensive to build turbines because the water depth is higher, and some areas in blue where it's cheaper to build turbines. So this was never considered in the optimization before. So normally they were just optimizing on annual energy production and then adapting manually the layout. Instead, using our software, we are able to balance these 2 tendencies, the one of maximizing the power production, but also considering the immediate cost. So with the black dots here, you see the optimized layout for this specific case. And if we go and compare our layout with the Vattenfall one, so here you have in black the optimized layout and in pink the one proposed by Vattenfall, you can see that there is a big gain by using our optimization framework. First of all, we're still able to produce more than the Vattenfall layout, about 0.28% more, but we're also able to save about 10 million euros in foundation costs by a smarter positioning of the turbines. So all in all, has been estimated by the company that this layout, using this layout instead of their layout, could have a gain of about 12.6 million euros in the lifetime of the park. Okay, so now we skip to the second point of the presentation. The voice is still fine, so. So the second block is the cable layout optimization. So what is the problem? So once we have decided where to locate the turbine, we have some turbines in the offshore area, and their energy needs to be moved to shore. In order to do that, what is normally done is that the turbines are connected to a collection point called offshore substation, and then the energy is moved from the offshore substation to the grid. So in my work, we focus on this optimization, so how to better connect turbines with the substation. And now we will see in the details why this problem is challenging and interesting. So focusing on this part of the picture, we suppose that the turbine are given, the position of the turbine is given, for example, by the optimization I just explained you before. We have the substation position given as well, and the electrical team of the company give us a set of possible cables that can be used in this connection. So what we have to find is how to connect all the turbines to the substation in order to minimize the total cable cost. So it's not only to decide which turbine should be connected to which turbines, but also what kind of cable to use in the connection. There are, of course, some constraints in this problem. The first one is that only one cable can exit a turbine because the energy is unsplittable. As I said, different types of cable can be used, and these different cables have different costs and different capacities. And Of course, when we decide to build one specific kind of cable, we have to ensure that the energy flow, so the current passing through that cable, doesn't exceed the capacity of the cable. We were also asked to avoid cable crossings. So cable crossings are not impossible in the reality, but they are not really suggested in practice. This is because, first of all, you need a specific structure, the one here in the picture, in order to lay one cable on top of the other one. And this structure is very expensive. The second problem is that even if you do that, you risk to damage the cable below. And having a damage in the cable can mean a lot of energy lost, and so has a very huge impact in money-wise for the company. So in practice, we were asked to avoid these cable crossings. In addition to also the substation has some limitation that translate in a maximum number of cables that can be connected to the substation. Another interesting point is to consider the cable losses. So when the energy passes through the cable, due to the resistance of the cable, part of it gets lost. So we also consider this problem. In this presentation, I will mainly focus on the basic problem as I explained it before, and just briefly tell you a little bit about how we consider cable losses in the optimization. Okay, so this problem is a problem actually on a graph. So this is a feasible solution for this kind of problem. All the dots represent turbines. The red square is the substation, and different colors represent different cables. You can see that this is a feasible solution because all the turbines are connected to the substation. The energy flows from the turbines, so from the dots, to the substation. So it's an anti-arborescence kind of graph. So we are given an input for this graph, the coordinates of the turbines, so the black dots here, the different kind of cables represented with different colors, and also how much each turbine would produce in order to understand what is the current, what is the flow and energy. So in our model, we use 3 different kind of variables. Fij are continuous variables that represent the flow, in this case the current, passing through a cable ij. Then we have xijt, that is a binary variable that is equal to 1 if the arc ij has cable type T or 0 otherwise. And then we have an additional variable yij that is equal to 1 if there is a connection, direct connection between I and j, independently of what kind of cable you want to use. So this is the model that we propose to solve this optimization problem. You can see that we are minimizing the total cable costs, and we are considering some flow conservation. This is constraint number 7. At the node, considering also the production of the turbines. We have the capacity constraint on the cables, and then the other cables define the limitations, so how many cables can exit a turbine, how many can exit a substation, and here C is maximum C cables can enter a substation. As you can see, the non-crossing constraint is not explicitly written in this model, and this is because we actually use an approach on the fly for this kind of constraint, where we also work a little bit on click strengthening. Okay, so in order to test how this model was performing, we used real data from the company. So we consider 5 different layouts, as said, from Vattenfall, from all over the north here, so from Denmark and from England mainly. And then we consider different cable sets, again, given by the company. So all in all, we end up having 29 instances for testing our model. So these are the results. So we can see that for some instances, this model is already working pretty nicely. So for example, for instances between 7 and 19, we are able to close the gap, so to find a proven optimal solution, and in some cases in a very short time limit. So we're talking about 2 seconds or 20 seconds. So this is very good. Nevertheless, there are some instances where finding a solution becomes really problematic. So in all the lines where you see a dashed line, this means that we weren't able to find any feasible solution given a time limit of 10 hours. So for those cases, if we were running Cplex after 10 hours, we wouldn't have neither a feasible solution. And this, of course, in an industrial setting is not feasible at all. So again, we realized that these instances were the most problematic one because or of some specific constraint that were highly constrained, let's say, for example, the maximum number of connections to the substation, or mainly because there were a lot of turbines involved, so the layout had a lot of turbines. So again, this was a problem of dimension of our model. So what we use is, again, to use a math-heuristic approach. So the first thing we did is to relax the model. So we allow this connected solution, but of course we highly penalize them. In this way, we are able to find in a very short time limit a feasible solution where to start from. So we take this initial feasible solution and we fix some arcs in this solution, and we re-optimize on the free arcs. And we iterate this process every time. So every time the MILP solver, in our case Cplex, is facing a model of a smaller dimension. Remember also that fixing an arc in our solution, so fixing that an arc exists, means also that all the arcs that cross with this arc are fixed to not existing, or variables are fixed to 0. So this actually reduces the problem a lot. How did we decide which arc to fix? Of course, this is an heuristic problem, and we designed 3 different heuristic strategies to decide which arc to fix. One is random, so we just randomly pick some arcs and fix them in the next iteration. One is distance-based, depending on the distance to the substation, and one is sector-based, where we span by sectors the area. So here I give you a small animations of the random fixing one, just to show you how this works. So we have our relaxed model where we say that it's fine to have disconnected solution. And in a very short time limit, here we're talking about 1 second, Cplex is returning on a feasible solution for this disconnected problem. So here you see again all the turbines need to be connected to the substation. And in this case, we also have an obstacle represented by this polygon. So once we have this solution, we randomly pick some arcs of this solution, and we fix them in the new one. So we fix the y variable to 1. This is, okay, so we take this and we feed it again to the optimizer, and this is what we obtain at the second step. So you can see that there are some arcs that were there before, and there are still in the new solution. Notice that the colors are different, because when we fix the connection, but not necessarily the type of cable that is used. So again, we take this solution, we fix some arcs, and we give the problem again to the optimizer. So this is different steps. Step by step, you see that the solution always improves, and of course gets more and more connected. So we repeat this kind of pre-processing, let's say, using all the different heuristics that I told you, and then we warm up the Cplex solver with the best solution we found so far. So these are the results. I'm sorry if they're really a little bit big, they're little, but you will, I guess, trust me on this. So here are again the 29 instances that we considered. Okay, for each of them, we solved them using our math heuristic approach with a different time limit. So 60 seconds to 24 hours. So you can already see that in about 10 minutes, this column over here, you don't have almost dashed line anymore. So it means that our heuristic is already able to find a feasible solution for all the problems. If you actually look at the value of this solution, you can also see that the gap is very small, so they are actually very good solution. And of course, using more time, you can improve this. But so this shows that compared with before, where in 10 hours we weren't able to find anything, now we have very, very good results using this approach. So very shortly, I will touch upon another problem that was proposed by the company. So in practice, when you buy the cable, these cables have different resistances. When the current passes through a cable, due to this resistance, part of it gets lost. In practice, what happens is that the most expensive cables are the one with the lower resistance, so the one that have less losses. So the question from the company, from the electrical team of the company was, would it pay off if we pay more at construction time to buy more expensive cables, and then we save on the long run because of these losses, so on the losses? Of course, this is not a trivial question to answer, because it's not only about the selection of the cable, but the selection of the cable may impact also the layout So how you connect the cables. So what we did to answer this question was to include these cable losses in our optimization. So I don't have time to go in the details, but what we did mainly is to notice that the number of possible cables are not that many in practical application, and the number of turbines that you can connect to each of the cables are not that many. So practically we can pre-compute for each kind of cable and for each number of turbines that you could connect to that specific kind of cable, what would be the revenue loss due to cable losses. So practically we pre-compute all these cable costs and we give them in input to the optimizer. So we are able to use the same model as before, but with a smarter definition of the inputs of the cable. So let's go to something practical, and let's see how these things work when we go in reality. So this is a real world cable routing from Onstre 1, a Danish park, and this was designed quite some time ago manually. So again, you can see that there are a lot of turbines that are connected to the substation over there. There are 3 different kinds of cables. The blue one is the most expensive and has a higher capacity, and the black one is the cheapest one, but can support only the current from one turbine. Here in the slide, you can also see the different prices in CAPEX, that is the immediate cost of the cable, so euro per meter. So what would happen if we propose to our model to solve this exact same problem? This is the solution we would obtain. So it's really different from the manual one. It's probably less pretty, but it's also way cheaper. It's about 1.5 million less expensive at construction time. If we consider in our optimization also the losses, we would obtain this other layout. You can see that is kind of similar to this one, but it's still a bit different, and it's still really different from the manual one. You could see that this second layout is still 1.5 million euros less expensive than the manual one from Vattenfall, but is also 1.7 million euros less expensive in 25 years when looking at the revenue loss due to cable losses. So this PhD was also very interesting for a continuous collaboration with the company. So as we have seen already in the problem of the cable losses, many times they were asking us, what would happen if I do this or if I do that? So we actually have quite some work about adding other constraints or other structures to our optimization. I won't have time to go through it, but I want to only give you an understanding of more or less what we have done more on these structures. So when we showed our solution to the company, one comment was also that we are not considering failures in any way in our optimization. And many times, they would like instead to have a more robust structure of the cable routing to consider cables. So in this example, if this cable would fail, the production of all the turbines would be lost. Instead, they want to have a feedback. And they also have a very specific idea of what kind of structures they want to have this robust layout to failures, and is a closed loop structure. And we will see it slightly in the next slide. So let's say we change our model, including also the possibility of having this specific structure to be safe from a failure perspective. We also had a lot of discussion about these branches in the layout. So there can be 2 options from the company, depending mainly on the kind of turbines that they decide to use in the layout. In some cases, they want to have only strings connection. That means only one cable entering and one cable exiting the turbines. So an arc constraint where this kind of connection is just a no-go. Another possibility is instead that they are fine of having branching, but those branches include some extra costs when actually constructing them in practice. So we also have both a version of the tool that imposes to have no branches and one that allows branches but consider explicitly the cost that those branches would have in reality. Finally, we also consider a very new yeah, a very new feature that's called offshore transformer module. So Siemens in the last year proposed a new kind of transformer that can be attached directly to the turbines, and this would allow to have OTMs, so the smaller transformer attached to the turbine instead of substations. So we also include this in our optimization model, and we had some tests about what is the impact in practice. So in this slide, what I wanted to tell you is that so the good thing of having an MILP model is that we were able to include all these constraints that came in a second phase. And from a company perspective, having all these constraints included is very important because they can take some informed decision that before they weren't able to take. So for example, if we look at the failure safe layout or structure that I told you before, in order not to risk from cable failures, they ask us to have this specific structure called loop structure or ring structure, where all the turbines are connected in strings, so only one cable entering and one exiting, and the strings are paired and connected together. So this structure is often used in the company, and when I was asking around, but this is actually pays off, or maybe it's better to change, to look for alternatives, nobody was really able to quantify what is this impact. While now we can include this in our optimization model, so having an optimized layout imposing this loop structure, and this is the one you have for this is an on-thread free layout. Or we can also optimize without considering. And of course, we can compare the two layouts and take then informed decisions. So for example, in this case, we came back to the engineers saying, okay, this structure would cost about 3.5 million euro more than if you use the basic structure. Is it a good option? Or maybe you can find something else like having generators on every single turbine. And so they can make some more informed decisions. So I'm at the end of my presentation, and I was very happy about this collaboration between the company and the university, because I think we managed to have contribution on both sides. So from a scientific point of view, we presented a new problem to the community, some new problems to the community that weren't really known before or not that deeply investigated, and we propose also some instances where to test them. This work has also a real impact in practice, as we have seen from our industrial company that is nowadays using these tools in its daily work. And of course, also scientific quality again, because we have been able to solve problems of large dimension that often appear in a different kind of optimization in our field. So that's for me. Thank you.
Martina, now we have a